Oh, it's 6 o'clock. I kind of spaced out. Welcome back, everyone. So to start us out today, are there any questions that folks would like to begin with? Okay, well, with where we're at so far in the course, we're at a pretty exciting time. We're just about done with chapter 4, dealing with regression. Then we're going to turn it over to dealing with probability theory. And we mentioned before, the reason for that is whenever we make an estimate that a population characteristic is approximately equal to a statistic like the sample mean, we have to describe the accuracy of that statement. And probability, in a weird way, is going to be the major tool that does it for us. It's going to be a longer chapter for us to get through. We'll take our time working through it. And for about, I'd say, a week and a half to 2 weeks, I'll feel like we're in a math course. It's kind of weird. In fact, when we do probability theory, we will use a calculator, but in a very, very basic way. The major things you need for your calculator for exam 2 are going to be knowing how to calculate summary statistics like sample mean, quartiles, medians, knowing how to calculate the correlation coefficient R, and coming up with the least squares regression line. We'll be going over those things today. But as far as probability goes, the calculator isn't the most big help. It'll just be for crunching out a couple fractions, things like that. Well, any questions at all, folks, before we jump in? Okay, well, let's take a look at where we're at. We're on example 3. But before that, here's a reminder on just what's going on in the calculator. The calculator is doing a lot of work for us when it comes up with a line like this one, this Y line. And essentially what it's doing is, we look at the color coding here, the Y1 is a real data value right here. This A plus BX1, that's just a point on the line, and that's the predicted value way down here. So the calculator finds the distance between the real value and its predicted. It takes that distance and squares it. That's why you see a power 2 right here. And then it adds all the squared deviations or distances from the line. We come up with a rather large sum, and the calculator is going to find the minimal sum so that the one line, there's a unique one, has the minimum sum of squares. It's really kind of magical in a certain sense. Any questions about that idea here? Okay, then we put this to good use. We modeled these data here. We threw a line to it, and that's really fast, basic questions relevant to it. And our goal today is really just kind of practice it again. Our upcoming quiz, let's take a look, is quiz number 6. I wrote this morning. I already kind of forgot. Yeah, it's another one of these. So what we're about to do is essentially just like what you see here on this upcoming quiz. This is also about what the format for a real exam question might look like. So you'll have some graphics, some of the raw data so you can put into the calculator if necessary. Then any kind of basic questions are down here. You can see us solving those once we're in example 2 or example 3. So if you're getting stuck on that quiz, take a look at the notes here, and I'll also be very happy to help as usual. Well, here's our next situation. Let's see, this particular example is a lot of reading, and it's also, to me, a big challenge when it comes to statistics. We have to absorb this context to know what's going on. And even part A, I mean, that part A reads like a book itself, but if we ignore the context, everything else gets a lot more fuzzy and a lot more difficult. So let's take our time and break this down. So it starts off with a big chunk of words just telling us the context of this problem. It says the authors of the paper, statistical methods for assessing agreement between two methods of clinical measurement. So it looks like we're dealing with hospital type situations. This was in the International Journal of Nursing Studies in 2010. So these data are somewhat recent at least. And here's what they did. They compared two different instruments for measuring a person's ability to breathe out air. And that's really critical in a clinical situation. If you go to a hospital and you're not breathing quite right, you might have serious pneumonia, something like that. And they want to know right away, how's your breathing function depending on the problems you have. So here's the situation. It says we have two instruments that were being considered. There was a right peak flow meter. Has anyone heard of that kind of device before, just out of curiosity? Awesome, some people have heard about it. If you're curious, let's take a look at a picture of that right now. For me, reading this problem, I was not quite sure what I was getting into when I read that. So right peak flow meter. Let's just take a look at all the images here. This is what we're getting into. So the idea is you take one of these devices, some of them look old or just more bulky or maybe more accurate. You blow through it and it's just going to measure how strong your lungs are once you do one of these kinds of tests. So that's what's going on with the context right here. So there's a right peak flow meter and a mini right peak flow meter. Well, that's kind of interesting. It says next, 10 people participated in the study, and for each person, their airflow was measured once using the right meter, so this one right here, and once using the mini right meter, so this one here. And well, now we have data. There's two numerical variables. This is just our identifier column. And already it seems kind of strange. There's a small measurement device. There's a ordinary measurement device. And their values are all close. If we highlight any row, they're about the same. So we wonder, what is this problem all about? And part A is going to address that right here. Part A says, suppose that the right meter is considered to provide a better measure of airflow. So that one's better, the one on the far right. It's more accurate. So the question I would have at this stage is, well, why do we care about the mini one? If the right meter is more accurate, throw this one away. It's useless, right? But that's not the whole story with this problem. It says next, but the mini right meter is easier to transport and to use. So that could be critical if you're, say, interested in Doctors Without Borders. If you're going into remote locations, you might be required to pack something that's less precise just because it's more portable. So now here's where the statistics comes in. It says, if the two types of meters produce different readings, but there is a strong relationship between the two readings, it would be possible to use the mini right meter to predict the reading that the larger right meter would have given. So imagine you're in some remote location, you allow people to use a mini right meter. But if you know how they're associated with the right meter readings, you could just calculate a formula and get the more accurate value from that, even when you have the less accurate device. So it says here, use the given data to find an equation to predict right meter reading using a reading from the mini right meter. So now that's the full context. Any questions at the moment with the story of this problem? Okay, this one's tough to get started since you might have noticed, usually the first column is the variable x. That's a pretty typical thing, but it's not always a guarantee. And this wording right here helps us to make sure it really is going to be the variable x. It says, find an equation to predict right meter reading. The thing you're trying to predict is automatically the response variable or the dependent variable. So that means this one right here is our variable y, which means we'll put in there L2. So the thing you're trying to predict is your response using a reading from the mini right meter. That's going to hopefully explain the value on the right here. So this one will be our explanatory variable. Put this one in green, as is our pattern so far on these notes. So we'll think of this column as being the x variable, which means we need to store that into L1. So with that all set up, we can finally start the problem. Let's import these data carefully and accurately into the calculator, and we'll be able to do this portion. We'll find that equation that gives us the prediction. In other words, they're just asking us for the least squares regression line on this problem. Okay, I'll get quiet while we're importing the data. But just as a reminder, first thing you'd want to do is hit the stat key and enter, and then delete anything that's there. Sounds like we just about have it. Let's just take a few more moments. Okay, if we're all satisfied with our data, next thing to hit is stat key just immediately, right arrow over to calculate, and we want option number 8. The shortcut here is you can just press 8 on your keypad right here. I'll scroll down to it and hit enter. I mean, that works just as well. Then hit enter loads of times until it goes to calculate. Then that's finally our output right here. It gave us y equals a plus bx, the value for a, which is the intercept, the value for b, which is going to be the slope. Gives us r squared, which we haven't discussed in this course, but also gives us the correlation coefficient r, which is pretty useful. So if we take all this information, I'll just take a screenshot and make sure the red dot's not in there in the screenshot. And here's what it would look like in your calculator. But what you would put down on paper, if it was, say, a quiz problem, web assignment problem, or exam problem, would be this. Either write y, or the best practice is y hat, but I'm not very picky about that. We need to give it first the a value, 120.95. That's rounding to 2 decimal places like the problem indicated for us. Then give it the value of b, which goes 0.75. It's positive, so plus 0.75, multiplying x. So we've got it, folks. We just needed to pull out this value and this value, plug it here and here. And then let me put a box around this one just to emphasize, as soon as you put that down on paper, you've got the right thing. Any questions, folks, on producing that regression line? Awesome. Do we feel like this is not too bad to do on an exam? Terrible. I kind of understand. On an exam situation, if it's 10 observations, that's already 20 pieces of data. So this is kind of a time killer on a real exam question. On a real exam question, I would probably make it go more like that, just to shorten it up. So if we're happy with importing 10 values, it's a little bit less of a bother. Then go from here, write that down on paper, and you'll be all set. Well, any questions or comments at the moment, folks, with getting that line? Okay, now that we have that line, we expect a few follow-up questions to go along with this. And let's go down and see what's coming up next. Right away, now that we have a regression line, they want us to find what would you predict for the right meter reading. That's going to be the value here on the far right. For a person whose mini right meter reading is 500. So let's take a look. They gave us a mini right meter reading of 500. 500 would go right there for the explanatory variable. And what we want is the response predicted given that value. So imagine you went to some remote place, you use your mini right meter, and someone tested at 500. But just to be a little bit more accurate, we're going to use this regression equation that relates the more accurate, heavier device and see what the more accurate value ought to have been. So it'd go like this. We take y hat, the predicted value, is 120.95 plus 0.75. We'll multiply this by x, and they supplied us the x value of 500 for the mini right meter. So 500 would go right inside here. And this is a good moment to pause as well. If this was a quiz problem, this is essentially our quiz problem, quiz number 6, then a good way to get partial credit is show me this right here. If I know what goes into your calculator, then I have a very, very strong basis for partial credit. And even if I completely mess up the calculator, maybe I didn't put in that decimal, and now my answer is way, way off, then I can still give loads of partial credit. I'll assume it was just a silly calculator mistake. I make lots of those too. So just a standard reminder on quizzes and exams, if there's a lot being calculated, this is worthy to put down on paper. But now let's go and calculate it for real. It's 120.95. Add to it, oh no, yeah, that was plus 0.75. I thought I hit the division key. times 500. So the predicted right meter reading should be 495.95. Well, we did, folks. That's our first prediction on this regression equation right here. And we can make all sorts of other kinds of predictions like these, but there's certain ones we can't make. We'll discuss that on the very last portion of this, part E, which also happens on the quiz as well. Well, let's try this again. But first, any comments at all on obtaining that value, 495.95? Okay, so now it says, give a practical interpretation of the slope using the context of the study. To me, this is always where it gets a little bit tricky. We need to go back to our regression equation, and we have to decide between these two numbers I'm highlighting temporarily in yellow. Anyone see which one is the slope between the two? Absolutely. The slope is always the one that is attached to x. It's the coefficient to x. So we'll say here, the slope is equal to the 0.75. And automatically, the first thing we want to do is make that a fraction. We'll put 1 down below, which is always valid when it goes into 0.75, exactly 0.75 times. And next, we throw in our units. So a reminder, we go right up here. I'm just going to take a temporary screenshot. The best way to get the units is knowing that the units for the numerator is always the y variable. So I'll put here for the numerator, 0.75. Let's see. They didn't tell us what the units were exactly, so I'll just say units for right meter. Then the denominator units are always the units associated with the x variable. So we can say down below, 1 unit for the mini right meter. So now that we have that down, this is not the practical interpretation. This is just the helper to it. If you didn't put down this step, you wouldn't lose credit, but I would assume that you're pretty good at this, so you didn't worry about that extra step. If it's a little bit foggy and a little bit confusing, this is absolutely worthy of writing down on paper. So here, we'll put down the practical interpretation. I'll write it like this just so that when you come back to the notes, you'll know right here, that's where we interpreted the value. And pretty much here's how it goes. We imagine the denominator increasing by 1 unit. So we'll say to start off, for each 1 unit increase for the mini right meter, we go on and say we expect the units for the ordinary right meter, the bigger device, to increase by that quantity, 0.75. So I'll say here, that's a lot of writing. We expect the right meter to increase by 0.75 units. Again, they never told us what the units were, so I'll just say units generically. What we've done, folks, that's our practical interpretation of a slope. We've only done this 2 times. Does it make sense on how we broke down this equation here into the interpretation? Okay, it really is definitely kind of a procedure. Start off by writing the slope, grab the units just like we did, see the color coding to help out when you're doing it on the quiz. And the interpretation is always that same kind of formulaic response. You can change the wording around if you like, but as long as it contains this kind of essence, you'll be in great shape. Well, we've done it, folks. That's our part C. And now part D is asking us, does it make sense to interpret the y-intercept? This one's tricky, and we mentioned on our last problem it did make sense to interpret the y-intercept when we were looking at the algae and the grazers on it, but that's not the case on every single problem. I'll leave it up to you to decide what the situation would be for the upcoming quiz. But now for part D, let's work our way through this. It says, does it make sense to interpret the y-intercept? So we need to find the y-intercept. Like you all said earlier, the 0.75 was the slope. So that means this quantity is the y-intercept, the 120.95. How do you get the y-intercept out? Instead of putting in a value like 500, you have to put in a value of exactly 0. Let's start by saying that. At the y-intercept, x becomes 0. Now let's stop right there and think about that. Does it make sense for x to be 0 in this case? Any volunteers for the situation here? Or maybe another question is, what was x in the first place? This is where statistics gets tricky. I just wrote down a variable, but we need to recall every time we answer a question like this, what did x actually represent? Let's scroll up to the top for the moment if we need some inspiration. X was this right here. It was the value when someone used a mini right meter. And so at an x-intercept, x has to take on 0. So someone put the right meter device up to their face and they got a value of 0 units. What would that mean about the patient?
They're dead.
They're dead. That's a medical emergency, right? This is a case where a value of 0 doesn't even make sense. Just dial 911. Don't do the statistics problem. We have a medical emergency on our hands. Does that make sense to folks? What's going on with this one? Yeah, go ahead.
Because the right meter or the mini right meter like is starting with the minimal value, it's like 380. Is that like a indicator that it should not be going back down to 0?
Yeah, absolutely. It's not a full indicator on every single problem. Even if 0 is not in the range of the data, we could still interpret it, although the interpretation would be called extrapolation, we'll say later. So always take a look at the range of the data, because that issue with extrapolation is going to come up on one of the next problems as well. When we did it before on this problem, we put x equals 0 and we said 0 just means there are no grazers eating the algae in the test tube, and that's completely fine. So even if 0 was really far away from all the data, we could have still given the interpretation. But this time 0 is close. It's just 1 unit to the left. So it wasn't even extrapolation this time. This is pretty good information. But yeah, that's a really good comment to make. If 0 is not even in the range of this, it may not make sense. We have to think about it really clearly. We could possibly interpret it, but this is a case where the interpretation wouldn't even make sense. It's just not in the spirit of the problem. The patient's not breathing. CPR is probably what they need to be doing next. So let's say here, when we give our explanation, at the x-intercept, x equals 0, this means, I'll say what folks said at the start of the class, the patient is dead or just not breathing. Let's go with not breathing. That just sounds less severe. And so the y-intercept does not make sense in this situation. So that's 2 interpretations down. And these are always pretty tricky, I'd say. The slope is not as bad because you can always interpret it. It always makes sense. And there's a real procedure to it. Write down the fraction, put it in units, and just explain as the unit denominator goes up by 1, so does the numerator. But this one, you have to keep very, very careful track of what the context was even saying. And again, that's the challenge of this problem. The context is huge. I can never actually make this an exam problem because it's not just putting all of this in the calculator, which does take a while. That's a lot of reading. I try to make my questions a little bit more shorter on a real exam where we have time to absorb all that information. But now we have time for one more kind of computation. Part E says, Explain why we should not use the least squares regression line to predict a right meter reading, just like we did up here in part B, from a mini rate meter of 250. And that was going back to the comment you were making earlier. 250, well, there's no trouble. You could put it right there and crank it out. In fact, let's see, do we have our calculator still warmed up? Yeah, we could go up here, put in 250 where we threw in 500. And there's our value, 308.45. But we really should still not do that. And like you were mentioning, it all has to do with this original data right here. So I'll take a screenshot of this column as part of the explanation. So what I would say for here is, oh, I color code this really crazy. Let me change this around. That should have been blue. So now here's our trouble. The minimum of these, I think you said earlier, is 346. So there's the minimum. The maximum is at 600. Oh, there's a larger maximum here. I think I see a 658. So now we can say any X value, much like the X value 250 that was supplied, that is far from the range of 346 to 658 is considered extrapolation when we use the so-called least squares regression line. So extrapolation is really very dangerous for us because our patterns that we're taking a look at, they're linear, they're straight line patterns, but only for a certain range. Let's take a look at even in just this calculator. We have all the data, so if we want to view it, hit the zoom key, and I believe it was number 9, but let me double check on that. Yeah, it's number 9 for zoom stat. Here's what our data looks like right here. And sure, you could put a straight line pattern to that. Here we go. But there's no reason to assume that this linear relationship were to hold. We go very, very far off to the right, or in this case, 250 would be very, very far off to the left here. The pattern might change. We're not really sure until we actually test the data in those ranges. So for that reason, we call it extrapolation. And any value that we try to extrapolate on should not be trusted. It's a best guess, but it is much worse than doing this right here. Here we have a little bit more certainty because 500 was contained within the range of the data. So here we can say any X value that's far out is considered extrapolation when we use the least squares regression line. And we should never trust the results of extrapolation, especially when it's quite severe, like in this case. 250 was well under the 346 minimum. If we were to take a prediction of, say, 330, that wouldn't be too bad. At 300, we're starting to extrapolate already. And at 250, we just should not even trust those values. Well, any last questions, folks, on getting through this problem? Okay, again, this problem right here is kind of a tough one because we're essentially just doing math. The statistics was right here when we imported the data, cranked out the equation. But this was a mathematical substitution. Here we're interpreting a mathematical slope and so on. So when we go to solve this, so again, another reminder, quiz number 6 in Moodle is very similar to example 3 and example 2 we just got through. Well, let's save these up. And I did have a question for the class. I don't have a problem prepared for today, but would folks feel like another one of these would be helpful just for the sake of practice? Or do we feel like we've kind of got it? Any volunteers one way or the other? Another one? Okay. So what I'll do is when we come back on Thursday's class, we'll start off with another one of these just for a quick refresher before we go back to wherever we leave off on chapter 5. So I'll put here another 4.2 question. Okay. I need post-it notes or else I'll say things and never remember to do them. But I think that should work. And now let's save this up and we're going to go to chapter 5 next. Okay, 5.1 is actually pretty fun of a section, I'd say, as far as statistics goes and WebAssign as well. 5.2 is still kind of a warm-up section, but the major sections, which we're going to spend the most time on and are a little bit tough, are going to be sections 5.3 and sections 5.4. So think of 5.1 and 5.2, the ones that are available on Moodle right now. They're just kind of the introductory topics before we go into the deeper questions. So it starts off by a really fast definition of probability. It says probability, whenever we say it, is a number between 0 and 1. You know, that's not the full story, and we've hinted at this before. I'll put it down on paper right now. It doesn't really have to be between 0 and 1 because that's a unit choice. You could also say between 0% and 100%. So if you like working with percentages, there's no harm in saying probability is a statement of chance where some kind of outcome is going to occur between 0% of the time and 100% of the time. In probability theory, we often use the decimal form of the percentage only if we're doing extra computation, since computing with percents can often give you the wrong values. So here's our initial example. It says we're going to toss a fair coin. What we mean by fair is we're thinking every time we toss it, we should get heads the equal number of times as we get tails in the long run. In the short run, if we toss it 10 times, anything could happen, right? You could, well, it'd be very rare. Maybe you should buy a lottery ticket, but you could get 10 heads or 10 tails in a row. But a lot of people are probably going to get things like 3 heads or 4 heads, the rest tails, and so on. So we're going to toss a fair coin. We expect equal heads, equal tails in the long run. And we're asked right away, what is the probability that the coin lands when facing head up, facing up? What is the probability when the coin lands facing down? Well, that's not too bad of a question. Any volunteers for the probability of getting heads? Exactly, it ought to be 50%, right? So this is kind of like the best question to start off because probability is a weird subject, so we need to anchor it to something we're familiar with at least, tossing a fair coin. Here's how we're going to rank these results in probability theory. When it says land with heads facing up, we often like to associate a symbol to that so that we're not always writing so much when we go to deal with the equations. So we're just going to call that H. H for you tossed a coin, that was our random experiment, and we got heads. When it says what is the probability the coin lands with heads facing down, let's give that a new symbol. We'll say that that's the event that T occurs. T for tail. If heads is facing down, you've got tails facing up. And then when folks said probability of heads is 50%, we would write this down. P is going to stand for the probability function. If you've taken college algebra, it's not too different from writing down, say, f of x equals 3x. If you've never taken college algebra, no worries. We'll discuss what we mean exactly by function. So the probability function takes an input. So we put parentheses around it. It doesn't mean multiplication. It just means the probability of something. We give it the event, H, or we could have just said probability, heads facing up, but this would be more typical. And then either say 50%. I'm completely fine with percentages, so I never worry about that on a quiz or exam. Sometimes WebAssign wants specifically the decimal number. If that's the case, take your 50% here, move the decimal point 2 spots to the left, and you get 0.0, let me try again, 0.50. So we could say the probability is 0.50 or 50% chance. Likewise, if we go to this event, heads facing down, we would write this. And this would just be read as the probability of the event T is equal to, well, it's 50% as well, or 0.50. So we did it, folks. That's our first probability question right there. Any questions or comments with the computations here? Okay, really all that happened on example 1 is we're getting used to the notations, the symbols that we're going to be using, things like P standing for probability and so on. So nothing too major happened on this one, but what we need to start doing is breaking down exactly what's happening with P as a function. So let's go to the next concept. Where we can actually calculate something like example 1, where we just had intuition of what the probability should be. So when we go to compute stuff, a lot of times we're really just taking this point of view in probability. It says the probability of some outcome, like getting heads or tails, denoted by probability outcome, just like when we wrote probability of H, to stand for probability of heads, is interpreted as the proportion of time the outcome occurs in the very long run. So flip a coin thousands of times, millions of times, we're expecting heads 50% of those times. So in this example 2, it's kind of a weird one because computation's already happened. We'll see how to do these computations section 5.2. And we're dealing with a standard deck of 52 playing cards that is shuffled well. The shuffle well here is the same as saying a fair coin. We don't necessarily know what's going to happen when we pull off the full card, the first card on the deck. And just like with a coin, if you flip it, you don't know where it's going to land until it lands. There are 13 spades in the deck. I wouldn't have known that unless the problem told me. And don't worry about too much of this. If you're not great at gambling, playing cards or roulette or anything like that, I don't bring in a lot of these problems. This will be one of the few. So it says the probability of selecting a spade at random from a 52 card playing deck is calculated this way. Because it was shuffled well, we're assuming that we have a fully randomized deck. You just take the number of ways to get a spade. There's 13 different ways. Divide by the number of cards in the deck, 52. And this is the result we get after reducing. 13 happens to go into 52 4 times. And we get that value right there. So the whole purpose of example 2 is, it's awesome to be able to calculate a probability statement like this. But if you calculate a probability statement and we're not sure what we calculated, then all of it becomes pretty much useless at that stage. Very often, especially when we're in chapters 6, 8, and 9, which are coming up actually not too long, in a few weeks, we're going to be giving these practical interpretations once we do a probability computation. And this is also very formulaic. The way I would interpret it is start on the right-hand side. You could leave it as a probability of 0.25, but if it's a practical interpretation, just like in class today, most people are going to say a percentage, right? Like when we said there's a 50% chance of getting heads. So over here, if you see a 0.25, we should start by saying there is a 25%. All I'm doing is taking that decimal, moving it 2 spots to the right, obtaining a percentage. So there is a 25% chance that, well, something happens. Anyone know what the something would be? Exactly. We go here, convert it to a percentage for our interpretation, but then go inside here and just say what the event was. There's a 25% chance that the randomly selected card is a spade. And we could do this experiment, say maybe 5 times. shuffle a deck really well 5 different times, pull out a card, and see how many times we get a spade. It's probably not going to be 25% exactly, but what we're saying here is, if you keep on doing this over and over and over again, then in the long run, it will settle down to 25%. Keep on shuffling your decks, and you will have a 25% chance in the long run of pulling a spade on your first pull of that deck. Well, we did it, folks. That's our practical interpretation. The computation was done for us, but no worries, in 5.3, we'll do one just like this. Any questions or comments at the moment and getting through that interpretation? Okay, this next part B, it's kind of an interesting spot. Part B is a problem that we're going to be using for this purpose. Hypothetical 1000 table. This is in sections 5.3 and 5.4. So the whole purpose of part B is kind of a warm up to the procedure we're going to be using in our text to calculate probabilities. Hypothetical 1000 table might not make a lot of sense just yet. We're gonna have to get to those sections. But the hint is this right here. We're going to consider something happening 1,000 times. So part B says, suppose that a card is selected at random from the well-shuffled deck of 52 cards, and assume we're going to repeat this experiment 1,000 times. So you select a card, record the result, reshuffle the cards, then select a card, record that result. You now have 2 results, shuffle again, and keep on going until you have 1,000 different results. Now the question is, how many times would you expect a spade to come up if we really did this? It would take a while, but any volunteers for how many spades we're expecting? Close. It wouldn't be a percentage, or depending on how you mean, it'd be a 25% of 1,000, exactly. We take the probability, 0.25, and if getting spade once is a 0.25% chance, just multiply that 1,000 times, and that will give the answer we see. So the process goes like this. For how many times should we expect a spade? If we repeat this all 1,000 times, we'll take 1,000 times the probability of a spade. This would be 1,000 times this value, 0.25. And already there's a definite warning about this. If we're doing interpretations, percentages are great right here. But if we're doing a computation, we must have the decimal form. If we put this in as 25%, literally, we would not have gotten the right value. So use decimals for computation. And for doing an interpretation, percentages are absolutely wonderful. Everyone will be more likely to understand what you're saying if you say it as a percentage. So use percentages for interpretations. Well, we just about have it, folks. If you take 1,000 times 0.25, now we're just moving the decimal spot 3 units to the right, so we get 250 spades. And this weird little action of taking 1,000 times a specific probability to get a quantity, that's going to be our major workhorse for doing probabilities of more complicated events. So we'll see that in sections 5.3, 5.4. Any questions, folks, on our computation here in part B? Okay, well, so far so good. So now we have an interpretation of what we mean by probability through example 2. So think of example 2 as just more of the definitions on what's really going here. Where do these numbers even come from? It's from this interpretation right here. Value settling down in the very, very long run. Next thing we need is, if we're going to calculate more interesting probabilities, we need some basic formulas that we're going to be working with. So first formula we're going to be dealing with is the probability of any outcome is a number between 0 and 1. That's just the restatement of the original definition we had at the top of the notes. Property number 2 is also helpful for us. It says, if outcomes can't occur at the same time, if there's no overlap, then the probability that any one of them will occur is the sum of their individual probabilities. Now let's say what they mean by that. In example 3, we have 4 different kinds of outcomes. There's a hardcover, paperback, digital book, and audio book, but there's no way to have a hardcover book be digital at the same exact time. That's impossible. So if you ever asked what's the probability of selecting a hardcover or digital book, because these can't happen at the same time, you just add the probabilities together. Oh, not break the table. You just add the probabilities of 0.16 together with the 0.40 together. So that's the idea of that value right here, property 2. Property 3 says the probability that outcome will not occur is 1 minus the probability the outcome does occur. This one's a little bit more tricky, and it's called the complement rule. It's not complement as you look lovely today, different kind of complement. It's more a complement as the parts that makes up the whole, complements it to make up everything. So the complement rule is rule 3. And with what we're going to do is run through this example and just get a feel for each one of these probabilities. Maybe we'll try part A and then take a break for the last ones. Does that sound all right to everyone? Okay, so the context here says, at a particular college, a bookstore sells books in several formats. We can get hardcover, paperback, digital, or audio. And that's the table that they're giving us right down below. The manager of the bookstore, based on past sales, gives estimated probabilities that a randomly selected purchase from this store will be one of those 4 different formats. If a purchase from past sales is selected at random, kind of like shuffling the 52 cards or flipping the coin, we want to know what the probability is that the purchase is for a book that is ... digital or audio. So here's how it started off this problem right here. Let's start coding these up. We can call this H for hardcover. I probably wouldn't call that P because we use P for probabilities. So you might call it, say, geez, I don't know. How about B for paperback? Then this can be D for a digital book and A for an audio book. So part A is asking for probability of digital or audio. We can rewrite this as, what is the probability that the book is D for digital, A for audio? I will put in this weird symbol that we're going to be seeing. In place of or, we put a union symbol. That's a kind of a strange symbol. It comes from set theory. And it's just a way to say this event together with this other event. All we now do is go to the probabilities. A digital book had a 40% chance, 0.40. We'll go plus next. And the further hint is, if there's an or in your probability question, we'll use a union symbol right here in the probability statement, and it will convert to a plus once we grab the probabilities we need. So I grabbed that one, and we're going to add to it A for audio, 0.08. We get 0.48. And if we were to interpret it, we'd say there's a 48% chance that a randomly selected purchase from that bookstore was for a book that was digital or audio. So those are the kinds of steps we'll be taking. But even example 3, it's kind of a warm-up. We'll come back to the next ones when we come back on Thursday's class, after our follow-up problem on doing another regression analysis. Well, any last questions, folks, on getting through that, at least part A right here? Okay, well, have a great evening, folks. On Thursday's class, again, we'll do a regression problem and then come right back to here on the notes. We'll probably get into 5.2 as well.